Welcome! Welcome to the Plasma Physics course of TPFL. In the past module, we have given a rigorous definition of a plasma. We have seen that plasmas are made of electrons and ions, charged particles that move under the effect of electric and magnetic field. Now, these electric and magnetic fields are actually generated self-consistently by these charged particles that constitute the plasma. Well, if we want to describe in a self-consistent way, we have to at the same time describe the generation of this electric and magnetic field and the motion of the particles subject to that. This is a complex nonlinear phenomenon, and the analysis of it will be subject of the future lectures. Here, in these first modules, we will start from the simplest study. That is, we will assume that electric and magnetic fields are given, and then charged particles move under the effect of this electric magnetic field given. We will study what is the trajectory of these particles. And in the present module, we will start from the simplest scenario, that is of a constant in time and uniform magnetic field. By studying the dynamics, the trajectory of charged particles in this constant and uniform magnetic field, we will also learn about the magnetic properties of plasmas. And we will have the opportunity to introduce the concept of magnetic moment. So let's start. Let's start with the simplest case, the motion of a particle in a static and uniform magnetic field. What basically we want to do is to solve the Newton equation with the Lorentz force, basically with the P constant. And we will look at the non-relativistic limit. Well, this equation can be solved by using brute force, really by solving all components, all the three components, all the three coupled components of it, or by studying a bit into details the properties of the particle motion subject to the Lorentz force. And let's take the second approach. The first thing that we want to understand and estimate is what is the variation of kinetic energy. Well, we can study the derivative of the kinetic energy, the time derivative of the kinetic energy, which is given by mv perp mv dot dv dt. dv dt is given by Newton's equation, and is given by Q, therefore V cross B divided by M. Now V cross B is perpendicular to V. If we take the dot product with V, what we obtain is, this is 0. In other words, d over dt of the kinetic energy is constant, which means that V squared is constant. The second thing that we have to notice is that the direction parallel to the magnetic field and the one perpendicular to it are quite different. It's useful to decompose the velocity as the sum of a parallel and a perpendicular component. Parallel and perpendicular to B. That is, V parallel is defined as the projection of V along B, take into account the direction of B, and V perp is equal to V minus the V parallel component. We can project the Newton equation along the parallel direction, which gives therefore the variation, the time variation of V parallel, which will be equal to the projection of Lorentz force along the B direction, and this will be equal to 0, which implies that V parallel is constant. But we also have that V is equal to V perp square plus V parallel square. And as both V parallel is constant and V total is constant, then V perp is constant. Now, what we have is that the derivative of V perp is perpendicular to V perp. At the same time, the modulus of V perp is constant. The only possibility is that the particles is in the perpendicular plane is drawing a uniform circular motion, whose property can be obtained by balancing the centrifugal force with the Lorentz force, where we have introduced two quantities here, rho, that is mv perp q divided by b, which is the radius of the circular motion, that is also called Larmor radius or cyclotron radius. And this motion will be associated with a frequency that we will denote with omega c, that is given by v perp divided by rho, and is the frequency of this uniform circular motion that is also called cyclotron frequency. These are two fundamental quantities in plasma physics. What is the consequence of all these observations? Well, that a particle, a charged particle, in the presence of a magnetic field, of a uniform magnetic field, moves with a trajectory that is a helical trajectory. Basically, its motion in the direction parallel to the magnetic field lines is not affected, while in the perpendicular direction it goes through a uniform circular motion. Okay, what I have drawn here is the case of a positive charge, and in fact for Q greater than 0 we will have a left-handed rotation with respect to B, while if Q is less than 0 we will have a high right-hand rotation with respect to B. In this particle motion we can observe that there is an instantaneous center of rotation that moves, in this case, in this simple case, in the direction parallel to the magnetic field. That in this simple case moves with a uniform motion along B. Just by looking at this simple case, by this motion of these charged particles in the magnetic field, we can infer the properties, the magnetic properties of a plasma. So, as we have seen in the presence of a magnetic field, this is the case of a positively charged particles. And now a charged particles, therefore, what it does here produces a current loop. As we know, there is a magnetic moment associated with a magnetic loop. What are the properties of this vector magnetic moment? Well, its intensity is given by the current times the area of the loop. And in the present case, the current will be given by the charge times the frequency, cyclotron frequency, divided by 2 pi multiplied by the area, which is pi over rho squared. And if we substitute the correct expression for omega and for rho, we obtain that this quantity will be equal to the mass times the perpendicular velocity squared divided by 2b, which is the perpendicular kinetic energy, divided by b. The direction will be opposite to b, both for q greater than 0 and q less than 0. In other words, this magnetic moment vector will be something directed like that. So what is the consequence of all this? That actually, because of the motion of both negative and positive particles, the magnetic field imposed externally, applied externally, will be reduced by the motion of the charged particles in a plasma. In other words, plasmas have the magnetic properties. In other words, the plasma tends to reduce the amplitude of externally applied magnetic fields. Let me make an observation about the magnetic moment. In fact, magnetic moment is an adiabatic invariant. What do I mean with this? Let me just remember a result that is given by analytical mechanics. In fact, the analytical mechanics books tell us that the action, let's call it J, that is given by the integral of P dq of a coordinate q and its conjugate momentum P. Well, J, this action, is constant, or better we will say is an adiabatic invariant under a slow change in an external parameter. This is valid under the assumption that the motion is periodic if there is no change of an external parameter. And we have indicated with this integral, the integral over one period. What does it mean? Well, let's suppose that we have a motion of a particle that is periodic. For example, the motion of this particle in the presence of a magnetic field. Then we evaluate this integral. And we find that this integral is constant even when you change slowly an external parameter that could be, for example, the magnetic field. Even when you change these external parameters slowly, then what you find is that although the trajectory of the particles can change because the magnetic field is changing, then this parameter will remain constant. What we say is that is an adiabatic invariant in the sense that it will be constant if the change of the external parameter is slow with in comparison to the period, to the frequency of the motion. Okay, in the case of the magnetic moment, let's see how we can apply this theorem that the analytical mechanics give us. Then we can take Q equal to X, and we will take one direction perpendicular to B, and the conjugate moment will be given by mvx. Now, if we evaluate the action of this coordinate x and its conjugate moment mvx, what we have is that this will be given by mvx dx, this expression here. We can divide and multiply by dt, which is therefore equal to mvx squared dt. And the integral in a gyro period can be written as the integral from 0 times 0 to time 2 pi over omega c. And then we can write Vx as V perp square and then with the oscillating component, omega c t plus a gyro phase, and this will need to be integrated over time. And by doing this integral, what we obtain is pi m v perp square divided by omega c, which is 2 pi m q by expliciting the cyclotron frequency, and this is equal to 2 pi m divided by the absolute value of the charge times mu, which is exactly the magnetic moment besides a constant factor. Therefore, what do we learn from this theorem of analytical mechanics? That the magnetic moment remains constant, this quantity remains constant here, even if the magnetic field can vary in time, can vary in space. Then if this variation is slow with respect to cyclotron period, then, and despite the fact that the trajectory of the particle may deviate, may change, this quantity will remain constant. In the present module, we have focused our attention on the trajectory of a particle in a fairly simple scenario, the one of a constant uniform magnetic field. We have pointed out that in this case, the trajectory of the particle is helical. And by looking at the trajectory of this particle, we have pointed out what are the magnetic properties of a plasma. In particular, we have shown that plasmas are the magnetic media. And we have also talked about the magnetic moments. We have shown that magnetic moments are actually an adiabatic invariant of the particle motion. In the next module, we will consider more complicated electric and magnetic field, and we will look at what is the trajectory of the charged particles in these.